Hello everyone. Welcome to the Learn Circuit tutorial. In this video, we will learn loop analysis, a method to solve loop or mesh currents. The main concepts are the follows. Loop, a closed path in a circuit. Inner loop or mesh. An inner loop or mesh is a loop that does not enclose any other loop. Loop current. The current goes through a loop. For example, in the following circuit, there are 3 loops. Loop A on the left. Loop B on the right. Loop C is the outer loop. However, for this circuit, there are only 2 independent loops. In fact, for all planar circuits, the inner loops are independent. I think the inner loops are self-explanatory. In this example, loop A and loop B are the inner loops, which is also called a mesh. When we use loop analysis, we only consider the inner loop, from which the KVL equations are linearly independent. Okay. The last concept is the loop current, which is the current that goes through a loop. We only label the inner loop current or mesh current, IA, and IB in this case. Note that loop currents are not real currents. The real current are on the branches, I1, I2, and I3 in this example. The loop currents are invented for loop analysis. Once they are solved, we can find the real currents. For example, IA is the only loop current going through the first branch, therefore, I1 equals IA. Similarly, IB is the only loop current going through the third branch, therefore, I3 equals negative IB. It is negative because the direction of I2 and IB are opposite. In the middle branch, both IA and IB go through it. In addition, because the direction of IA is the same as I2, and IB is opposite to I2, we will have I2 equals IA minus IB. Again, once the loop currents are solved, we can determine the real branch currents. Now, let's learn how loop analysis works step by step. Step 1. Label loop current for inner loops. Step 2. Write KVL for each loop. Step 3. Solve the system of equations. Now let's see an example. This is the same circuit we used to explain the concepts. We need to determine the branch currents. Step 1 is to label loop current for inner loops. Rule number 1. We simply label the loop current in clockwise direction for consistency. I will show you later that we will get the same solutions regardless of the direction. Step 2 is to write KVL for each loop. KVL stands for the Kirchhoff's voltage law. There are quite a few ways to write a KVL. The most intuitive way is that the summation of voltage rise around a loop is equal to the summation of voltage drop, as indicated as equation A. If we move the summation of voltage drop to the left, it becomes equation B. If we move the summation of voltage rise to the right, it becomes equation C. If we assume the voltage drop is negative, it becomes equation D. If we assume the voltage rise is negative, it becomes equation E. These are the 5 equations for writing a KVL. But I hope you realize that they can derive from each other. Equation A is very easy to memorize, but it is not very practical for writing KVL because you need to group the voltage rise and voltage drop first. I typically use equation B to write KVL, but you can just pick either equation B or C. There are 2 loops. We will write KVL for them one by one. For loop A, we will have VS1 minus, VR1 minus, VR2 equals 0. Note that we used KVL equation B. In words, voltage rise minus voltage drop equals 0. Rule number 2. The voltage across a resistor along the loop current direction is always drop. But why? This is because passive sign convention indicating that the current enters positive terminal of resistors. Now let's use the passive sign convention to explicitly label the voltage polarities across R1 and R2. For R1, the current enters the left, so the left terminal should be labeled as positive, and the right terminal is negative. Similarly, for R2, we need to label positive polarity at the top and negative polarity at the bottom. Once the voltage polarities are labeled, it is clearer that the resistor voltages are always drop along the loop current direction. For the same reason, we do not need to label voltage polarities explicitly. If this is not clear to you, I recommend you to watch the video on the passive sign convention. I posted the video link below. Rule number 3, for a voltage source. The voltage is rise if the loop current enters its negative terminal. The voltage is drop if the loop current enters its positive terminal. For example, for Vs1, the loop current enters its negative terminal, so it is rise. Therefore, in the KVL equation, Vs1 is rise, which has a positive sign. Vr1 and Vr2 are drops, which have negative signs. But what are we solving? Remember that in the loop analysis method, we solve loop currents. We need to express the resistor voltages in terms of the loop currents. We can use Ohm's law to do so. Because Ia is the only loop current goes through R1. We can express VR1 equals to Ia times R1. Because both Ia and Ib go through R2. We can express VR2 equals to Ia minus Ib times R2. Rule number 4. Because we are working on loop A, we call Ia as the active current and Ib as the adjacent current. If the adjacent current direction is opposite the active current direction, the final current will be the active current minus the adjacent current. If the adjacent current direction is the same as the active current direction, the final current equals the active current plus the adjacent current. Because Ia and Ib are opposite to each other, we have Vr2 equals to Ia minus Ib times R2. Finally, we can substitute Vr1 and Vr2 into the KVL equation. For loop B, we will have minus Vs2 minus Vr2 minus Vr3 equals 0. By applying rules 2 and 3, we will find that all the terms have a negative sign. The voltage across resistors are always drop, so Vr2 and Vr3 have negative signs. For Vs2, the loop current enters its positive terminal, so Vs2 is voltage drop and has a negative sign in front of it. By applying Rule 4, we can express the equation in terms of Ia and Ib as follows. Because both Ib and Ia go through R2. In addition, because we are working on loop B, Ib is the active current and Ia is the adjacent current. Therefore, for Vr2, we have Ib minus Ia times R2. Okay, now we have two equations with two unknowns. We can solve them in step 3. We will find Ia equals 0.625 amp and Ib equals negative 0.125 amp. Finally, we can solve the real currents. As we know, current has two pieces of information, namely direction and magnitude. So, we need to determine the direction first. Let's go ahead label the real current direction as shown in the circuit. We have learned the relationship of the real current and loop current when we explain the concepts. Based on that, we can find that I1 equals Ia, I2 equals Ia minus Ib, and I3 equals negative Ib. Alright, we learned 3 steps and 4 rules. Now, let's clean up the notes and try a different way to label loop current direction. We will get the same solutions regardless of the labeled current directions. We will use the same circuit. However, we will define the loop current for loop B counterclockwise and label the current as Ib hat. For loop A, we will have 6 minus Ia times or 1 minus Ia plus Ib hat times are 2 equals 0. The resistor voltage is always drops. so they have negative signs. For Vs1, the loop current enters its negative terminal, so it is rise. Now the two loop currents going through R2 have the same direction. Therefore, the voltage across R2 is IA plus IB hat times R2. For loop B, we will have 3 minus IB hat times R3. IB hat plus IA times R2 minus equals 0. Again, the resistor voltage is always drops, so they have negative signs. Again, the two loop currents going through R2 have the same direction. Therefore, the voltage across R2 is IB hat plus IA times R2. For Vs2, however, the loop current is labeled differently. Now, it enters its negative terminal, so it rises. By solving the two equations, we will find IA equals 0.625 amp and IB hat equals 0.125 amp. IB and IB hat are exactly the same, although their magnitudes are negative to each other. Their direction are also opposite to each other. Finally, we can find that I1 equals IA, I2 equals IA plus IB hat, and I3 equals IB hat. All the solutions are the same. My final note is that for this simple example, both ways of labeling loop current have their own advantages. However, for more complex circuits, labeling all loop current in clockwise direction is more consistent. Because for the resistors that have two loop currents going through, you will always have active current minus adjacent current times a resistor as the voltage. Okay, let us summarize. In this video, we learned the main concepts of the loop analysis. We then learned its major steps. We also learned the 4 rules. Finally, we discussed how to label the loop current directions. That's it for this video. I hope you find it helpful. If you have any questions, please leave a comment below. This example is also solved using the node analysis and superposition method. You can compare them to see which method you prefer. The links are posted below. Thank you for watching. Visit learncircuits.net for more information. See you next time.